Okay, everyone, welcome to another video lecture series on Physics 1. So today's discussion will be on impulse and momentum. Okay, so for this video lecture series, we will be presented with the following topics. We have momentum for two-dimensional motion, Newton's second law in terms of momentum, impulse momentum theory. Okay, so let's start with the first topic, momentum. Okay, so when we refer to momentum, we also are referring to what we call linear momentum. So, meaning this involves the quantification of momentum of motion of the objects moving along a straight line. Momentum is denoted by small letter p, and it is defined as the product of the body's mass and velocity. Now, in terms of the units, since momentum is would come from the product of the mass of the object and the velocity of the object, so mass of the object is expressed in kilograms and velocity is in terms of meter per second. So therefore, the momentum of p is kilogram meter per second as a standard unit for SI. Now, momentum is related to velocity, and velocity is a vector quantity. It follows that the momentum of an object is also a vector quantity. Now, a vector quantity wherein its direction is along the particle's velocity. Now, the corresponding equation for momentum would be P is equal to m times v. Of course, since the momentum of an object is directly proportional to m, at the same time it is directly proportional to v. This means the greater the mass of an object, the mass of a moving object, the greater its momentum. And the greater the velocity of the moving object, the greater its momentum. Okay, so it follows, since this is a product of m times v, if the object is not moving, meaning that the velocity of the object is zero, this means that the object has no momentum. So what is required here is that the object, in order for an object to have momentum, is for the object to be moving. Okay, so let's consider the following examples. Okay, so question, a car driving north 20 meters and an identical car driving east at 20 meter per second, which of these two has the greater momentum? Okay, so the answer is they have the same magnitude of momentum, but they have different momentum vectors since their directions are different. Now remember that momentum is a vector quantity, which means that the value of the momentum depends on the not only on the magnitude of the product m times v, but also it depends on the direction of v. So since it is indicated here in the question that the first a car is moving towards the north at a given velocity of 20 meter per second, and an identical car moving towards the east, moving at the same speed, 20 meter per second. So, given that the two has the same speed, but they are moving in different directions, therefore they have different velocities. It is said that the two cars are identical, so meaning they are assumed to have the same mass. So although they have the same mass, they have the same speed, but they have different velocities, so they have different momentums. Okay, so momentum for singular, momenta for plural. So correctly speaking, when the momenta of the two cars are not the same. Okay, so let's take on another problem. Find the momentum of a 50 kilogram boy running at 60 meter per second. So this is a direct substitution problem. So simply, to get the momentum of the boy, you just multiply 50 kilograms multiplied by 6 meter per second. So that gives us 300 kilogram meter per second. Okay, so no need for any attachment of the solution. So this is just simple multiplication of the number of the mass of the object with the velocity of the object. Okay, so we can express momentum of a particle in terms of its components, since momentum is a vector quantity. So just like any other vector quantity, a vector quantity could be expressed in terms of its components along the x, along the y, or if we're going to add another dimension, or the z dimension, we could also attach that also for the component of the momentum in that axis. So we often express momentum of a particle in terms of its components. If the particle has velocity v sub x, v sub y, v sub z, when its momentum components is p sub x, p sub y, and p sub z, then the overall value of the momentum is given by are given by, according to components, p sub x is m v sub x, p sub y is equal to m v sub y, and p sub z is equal to m v sub z. Okay, so let's discuss now momentum for two-dimensional motion. When we say two-dimensional motion, it is motion along two components or two axes, such as when the object is projected sideways along the air, the object is moving horizontally, at the same time it is moving vertically, or vertically going up or going down. Okay, so a momentum is a vector. Therefore, it is desirable to analyze them in terms of their components. Okay, so for example, you have a ball. For example, the ball was kicked in this given direction, indicated by its velocity. So, since velocity is a vector and momentum is a vector, so therefore the momentum and the velocity of the ball when it was projected in this angle has two projections, one in the x and one in the y, indicated here as v sub x and v sub y. Coincidentally, the momentum is p sub x and p sub y. Now, p sub y and p sub x serves as the component of our momentum of the ball, and v sub x, v sub y serves as the component of our velocity. Of course, the direction of the momentum is in the same direction as the velocity. Okay, so how do we now compute for the component of each, the momentum according to its axis? Of course, if the given angle with respect to the horizontal is given as theta, then the momentum of the ball along the x is simply m times v cosine theta, along the y, m times v sine theta. Now, let's proceed with the next topic, Newton's second law of motion in terms of momentum. Now, momentum is related to Newton's second law, since when a body accelerates or decelerates, the momentum will change. Since momentum is directly proportional to the velocity, or is related to the velocity, if there would be changes in the velocity of an object, therefore there is acceleration, there will be changes in the body's momentum. Now, of course, the changes in the velocity is indicated by the acceleration of the object, and as we know from Newton's second law, an acceleration is produced by a net force applied on an object. So a net force, or the sum of forces acting on a body, is equal to the time rate of change in momentum of the body. So how did that happen? If you're going to derive it, remember our formulation for Newton's second law of motion. We have the net force is equal to the product of the mass of the object times the acceleration of the object produced by this net force. Now, if the acceleration is defined as the rate of change in velocity, so we have v over t. So multiplying the numerator with m, so we would have m times v as our product. Remember our definition for momentum. Momentum is the product of the mass of the object times the velocity. So essentially, the product m times v is the momentum of the object. So therefore, our net force could be re-expressed in the form of momentum divided by time. So we know that anything that changes with respect to time is the rate of change of that quantity. So since this is momentum, the rate of change in momentum over time gives us the net force for an expression for Newton's second law of motion. Now, if the momentum difference happens between two specific values within a given interval, so our p here becomes p sub 2 minus p sub 1, or final momentum minus initial momentum. Okay, so moving on, we have impulse. When a momentum change, uh, what causes the momentum is indicated by Newton's second law, is the net force applied to it. Now, the change in momentum is specified in physics as a separate quantity apart from momentum itself, and we call this change in momentum as the impulse. And this is symbolized by the symbol capital letter J. Now, in terms of its definition, a force F that acts on a body during a given time interval t provides the body with an impulse. This is denoted by J. Impulse is also a vector quantity, meaning it has magnitude and direction, and is in the same direction as the net force. So whatever the direction of the net force, it would also be the same direction for the impulse. Now, in terms of the international standard of units for impulse is equal to has the unit Newton second. Okay, so as we can see here, that the the vector symbol for the impulse is capital letter J, is equal to the net force multiplied by time. If it happens that the momentum occurred within a given time interval between t sub 1 and t sub 2, we have the reformulation of the impulse as equal to the net force multiplied by delta t. Okay, so let's talk about more on impulse and momentum. Okay, so from here, try to cross multiply t to the side of the net force. So we have here the sum of the net force multiplied by t, which is essentially the definition of our impulse, this one. So in terms of the relationship of impulse with momentum, if the product of the net force and time is the impulse of the force, then this is essentially equal to the difference between the final momentum minus the initial momentum. So therefore, in terms of the relationship between momentum and impulse, impulse is simply equal to the change in momentum, just like what we have defined earlier. The momentum change is the impulse of the impulse on the object. Now, to further establish this idea, let us try to compare it with our definition for work. If you recall our discussion on work, work is defined as the product of the force and the distance, or the distance. So try to compare it with the formulation for the impulse. Now, force times distance. This is force times time. So, meaning whenever we talk about the application of forces on objects, we do not only consider how much force, how strong is the force applied onto an object. We do not only consider how far or how distant is the effect of that force applied to. We also consider the application of the force and the time it takes to apply that force. This means this actually tells us something about the effectivity of the force when it is applied to a given object. How effective is the force in changing the state of nature of the motion of an object. So for example, if you consider the time of application, this is actually the of application of the force. For example, if you're going to have a stalled car as an example, a car that suddenly stops because of engine failure. What happens when a car engine fails? Usually, the driver would ask someone to push behind the car So essentially, there is force applied behind the car, and of course, what matters is that the driver needs a certain amount of time for the car to gain momentum, meaning that the person or persons behind the car should be applying their pushing force behind the car at a given certain time, so that it would give enough time that for the driver to start the car. So of course, when you apply the force on behind the car, it is more effective when you apply the force in a prolonged manner, meaning that the time interval is large or extended. That would be more effective than when you apply the force at a very short interval. Of course, you will not be the people behind the pushing of the car would not be effective in starting up the car, or having the car to start to gain momentum if they're going to simply push on the car, just like when they are pushing on a button. So you just push on, then push off. So what you do is to continually apply the force behind the car in order to effectively move the car in order for the car to gain momentum. So that means you apply the force in a prolonged manner. You have to apply the force at a larger length of time, which makes it more effective. Uh, Comparing that with the application of force at a short interval, that the application of the force would not be effective. In essence, the application of the force for a prolonged period of time, or a shortened time, we refer to this quantity as the impulse. So instead of saying that the force applied is prolonged, or is applied at a short interval, we simply say the impulse is either large or small. Okay, so I hope that you get this idea. Now, in terms of the relationship between impulse and momentum theory, we already established this earlier. So the relationship comes from the idea that the cross multiplication of time with the net force gives us our impulse, and this is equal to the difference in momentum final minus initial, or the change, simply the change of momentum of the object. So just like what is stated, just like what we see here, the relationship between impulse and momentum is known as the impulse momentum theorem, which states that the change in momentum, this one, during a given time interval t, is equal to the impulse of the net force that acts on the body. Okay, so just like what we see here as the derivation. Okay, so let's have a sample problem for this one. Suppose you throw a ball with a mass of 0.4 kilograms against a brick wall. It hits the wall moving horizontally to the left at 30 meter per second and rebounds horizontally to the right at 20 meter per second. So find the impulse of the net force on the ball during its collision with the wall. And letter B, if the ball is in contact with the wall for 0.010 seconds, find the average horizontal force that the wall exerts on the ball during impact. Okay, so let's try to answer letter A. Find the impulse of the net force on the ball during its collision with the wall. So just like what we have presented earlier, that the impulse has two expressions. The impulse could either be found by getting the product of the force and time. So J is force times time. Or we could simply get the difference in momentum between the final value minus the initial value. Okay, so what is presented here in the given problem is that we are given the mass of the ball, so 0.4 kilograms. So definitely we could simply make use of this of the impulse momentum theorem in order to get the momentum, since we are obviously given the mass of the ball. So what we need is simply the mass of the ball and the difference between the velocities. Okay, so the velocity of the ball when it is moving towards the wall, moving horizontally to the left, is 30 meter per second. Okay, so the left direction is indicated by negative 30 meter per second. And rebounds, meaning after bouncing off the wall, the ball moves to the right at 20 meter per second. So therefore, we have the change in our velocity as negative 30 minus 20. Okay, so we have in our form of the equation negative 30 minus 20, so that gives us negative 50. So multiply that with the mass of the ball, which is zero point 0.4 kilograms. So you have zero point 0.4 times negative 50. That gives us negative 20 kilogram meter per second as the impulse of the net force. Okay, so I'm just describing to you the solution. I am assuming that you will be doing the verification of the solution on your own, writing perhaps on a piece of paper if you have a piece of paper with you, and your calculators as well. Okay, so even though it's not the actual solution is not presented here. Okay, so we're done with letter A. Let's now move on to letter B. If the ball is in contact with the wall for 0.010 seconds, find the average horizontal force that the wall exerts on the ball during the impact. Okay, so in order to solve now for letter B, what we need is the second form of the first initial form of our impulse momentum theorem. We have the definition for momentum, which is force times time. Now, since we already computed for J, which is negative 20 kilogram meter per second, the if we're going to divide that with the time of contact T, then we should be able to get the average force applied by the wall on our ball during the time of impact. Okay, so given that we already solved for negative 20 kilogram meter per second, we divide that with 0.10 seconds. That gives us 2,000 Newton amount of force that exists between the wall and the ball. Okay, so the answer is 2,000 newtons. Okay, so again, I am assuming that you are doing the same computation on a piece of paper and your calculators. Okay, so let's try this again. We have a second sample problem. A soccer ball has a mass of 0.4 kilograms. Initially, it is moving to the left at 20 meter per second. So 20 meter per second towards the left. So this is supposed to be negative 20 meter per second to indicate the left direction. But then it was kicked and was given a velocity at a 45-degree angle upward to the right with a magnitude of 30 meter per second. So the ball was kicked. The ball was initially moving towards this direction, towards the left. The soccer player kicked the ball, so it gives the ball a flight velocity of 30 meter per second, angled 45 degrees with respect to the horizontal. So what is asked here is to find the impulse of the net force and the average net force, assuming that the collision time is 0.010 seconds. Okay, so the solution here is almost the same as the solution that we have presented in sample number 1. So what we need to do is to get the amount of impulse during the collision time. We can find the impulse by getting the sum of the momenta before and after collision. So we have here as our initial velocity. So this would serve as negative 20 meter per second. So that is the initial. Whereas the final momentum would be the component of the 30 meter per second velocity times the mass of the ball along the horizontal. So that means we need to compute for 30 cosine 45. So again, I am assuming that you are following me using your pen and papers and your calculator. So type in your calculators 30 cosine 45. That gives us 21.21 meter per second. So that is the velocity, the final velocity. So expectedly, we will be we will be subtracting this from we will be subtracting the initial velocity from this value. So this means we have minus negative 20. So that means that becomes plus 20. So that is 41.21 kilogram. That is the velocity. We multiply that with zero point 0.4. That gives us 16.49 kilogram meter per second as the uh, momentum, or the impulse, or the change in momentum, or the impulse of the ball during the time that they collided, uh, during the time that the ball and the player's foot uh, collide. Okay, now next is to compute for the net force. So simply, once you have found or computed for the impulse, we simply divide that with the given time interval. Okay, so the given time is 0.010 seconds. So we divide 16.49 by 0.01 seconds. So that gives us 1,649, or 48.5. That is newtons. Now, one curious thing that I haven't pointed out for this problem is that the ball is actually moving in two dimensions. So this means that there are two components for the velocity for v sub 2, one along the x and one along the y. What we have computed here earlier as 30 meters cosine 45 is simply the x component of the velocity of the ball along the horizontal. That is the one that we added with negative 20 meter per second. So essentially, what we have computed is simply the momentum of the ball along the x-axis. Now, if we wanted to compute for the momentum of the ball along the y-axis, we simply get 30 meters sine 45. So that is essentially equal also to, so that is 30 sine 45 is the same as, is equal to 21.21, the same with the one that we have computed for the x component. Now, to get the overall momentum, we simply make use of the Pythagorean theorem in order to combine the two velocities. Anyway, we have already computed for what is being asked in this sample problem. Okay, so this is a simple linear momentum problem. You could apply here the impulse momentum theorem in order to get what is being asked. Now, for this problem, I'll be asking you to answer this problem as a part of your exercises. Okay, so this is to be submitted. Okay, so this ends up our video lecture discussion on impulse and momentum.